Hi, welcome to CSC/ECE 506. Today I will talk about parallel programming models in Chapter 2. It's a relatively short chapter, so I will only have one module. So first, let's look at parallel programming models. What is a programming model? Essentially, an abstraction provided by the hardware to the programmers. It's a way the programmers view the machine. For example, when programmers write their code, they don't have to know how many pipeline stages there are in a processor, what is the branch prediction mechanism used, how many cache levels there are and their sizes. They don't have to know how many functional units there are and so on. So it's essentially programming model is a simplified view of the machine. But it carries a very important implication. It determines how easy or difficult programmers can translate their algorithm into computation. There are programming models that have been used in single processor system, non-parallel system. This is essentially based on partitioning computation into program and data. And this is bundled in an instruction set architecture. So when we view the machine, essentially we view the machine as something that executes instructions. Now, uniprocessor programming model has been proven to be highly successful in hiding hardware from programmers. So much so that whenever we have a new processor architecture, programmers don't really have to change the way they write their programs. Now on parallel computers or multiprocessor systems, the programming model is not as clear-cut, it's not as transparent. There has been a lot of debate. There is still a search for the right one. Two of the most popular programming models is shared memory and message passing. Let's look at the difference between them. A shared memory model essentially treats the memory as something that is visible to all the processor or processor cores. All the processors can read from any part of the memory, and the memory is essentially a flat address space. Any core can write to the memory, and any core can write to anywhere in the memory. So, for example, if one processor wants to pass value to another processor, all it needs to do is to write that value to some location in memory, and another processor will read or load from that same location in the memory. And automatically data is passed from one processor to another. The alternative to that is message passing model. The message passing model is different in the sense that it assumes that processors have their own view of the memory, have their own memory, and they cannot see each other's memory. So in order for one processor to send a value to another processor, it has to explicitly perform a message sending, and the other processor has to explicitly receive the message. Okay. So let's see where they come from, or whether we know something analogous to that. Okay. So one way to think of shared memory versus message passing is to think about thread versus process programming in non-parallel systems. For example, a process or two processes, they share nothing. They have their own address space. They can't see each other's memory, and there's a good reason for that. By isolating processes from each other's memory, you cannot have one process corrupted or have security breach that affect the other process. So there is a good reason for that. For threads, on the other hand, they share the same address space, so they can see each other's data. Okay? They see each other's memory. There is only one address space. And there is also a good reason for that, in that the threads can communicate easily, and thread management, right? Let's say spawning a thread is cheaper than spawning a process. Alright, so here in the slide I show you an example of how to spawn a process. So the system call used for that is fork. So if fork is 0, then that code will branches to the child process, else it will be the parent process, right? So both the parent and the child process will be initialized to some program counter, and with their on their own address space, and the program counter will be different. The child will start with the printf I'm the child process, whatever program counter corresponds to that. The parent will go to the other printf, a program counter corresponding to that printf. So processes, as I mentioned earlier, are heavyweight. Processes share nothing, so if they want to communicate, they have to use socket, file, or messages. Threads, on the other hand, are lightweight and share one address space. One way to instantiate a thread or to spawn a thread in Linux, for example, will be to use the clone system call. Okay. In a clone system call, essentially you pass the function that the thread should execute, including the arguments, right? So once you call clone, the thread will start from the following program counter, which is the say hello. Okay. So that's pretty much the analogy for shared memory versus message passing. So shared memory programming model is like programming model using threads. Message passing programming model is programming model using processes. Let's look at some example. Let's some further example. Here I show you a code here where a thread will spawn another thread. We'll call that the child. The child will perform an addition and print out the result. Now, suppose that we start in a main function in a parent thread. So it initializes 5 and 3 to A and B. It sets the signal to 0, and then it performs a clone. So the child thread is spawned and start running. However, we want to make sure that, let's say, the thread executes after all the data is ready. So it will wait while signal is 0. It will wait in a loop until somebody sets the signal to 1. In this case, the main thread sets the signal to 1, indicating that, okay, child thread, now you can move ahead with your computation. So the child thread will go and print the sum of A and B, and then set the signal to 0, indicating my work is done. Whereas the parent process will be waiting for the signal to turn to 0. After that, it will print all done and then it exits. Okay. So in a message passing example, I have to do the same thing, except that the child thread doesn't automatically, the child process doesn't automatically know what's the value of A and B. So instead, we have to explicitly send a message containing the value of A and B, and the child process have to receive a message explicitly containing the value of A and B, and then assign that to its own local A and B. Okay? So the differences with the shared memory will be communication explicit, and synchronization, or the order of operations, are automatic. They are already implied by the message sending and receiving. Right, so let's compare them from the high level. So the communication is implicit in shared memory because we use loads and stores. In message passing, it's explicit. You have to use message send and receive. Synchronization, on the other hand, the message passing is implicit because the messages sending and receiving have a dual role in the sense that they act as synchronization, ordering of which computation happens before which computation. In a shared memory, because the communication is implicit, there needs to be an additional mechanism for synchronization. Therefore, synchronization is explicit. Now the next aspect is how much hardware support is needed. For shared memory, it depends, but typically it's required, especially if you want to build large systems. The complexity of the hardware support depends on the size of the system. Small system has less hardware complexity. On the other hand, message passing typically does not need special hardware support. It only needs the ability to send a message and receive a message. Now there's a lot of debate between which one is best for programmers, the shared memory or message passing. But as we can see, they do have different characteristics. So for example, in the development effort, a message passing program is typically more complex because from the get-go, from the writing of the program, programmers already have to think about how to partition data, which data is stored in which process, which data gets communicated to another process, and so on. In a shared memory, development effort is typically lower because programmers don't have to think about where data is stored. Every thread can see the same data. However, during the tuning effort, that's when all these things that are hidden in a shared memory actually matter for performance, and hence the tuning effort is higher. On the other hand, for a message passing, programmers already have to think about data layout, data partitioning from the get-go. So the tuning effort is easier. Right? So both the shared memory and message passing have different characteristics. And therefore, in my opinion, there is no clear winner. The shared memory programming models tend to be used for smaller systems. The message passing programming models are often used for larger systems. Alright, so I have discussed this one, so I'm going to skip this slide. I have another example here on slide 11. So here essentially I'm discussing what needs to be provided in terms of primitives in a parallel programming model for shared memory. So suppose I have the following code. I want to add, I have 8 iterations of for I loop. I want to add elements of array B and array C and put that in array A. And then I have another loop in which I want to check the value of array A, and then if it is positive, I'm going to accumulate that in sum. Okay, so remember that we use shared memory programming model. It means every thread or all the threads can see the same thing. Let's take a look at the code. First of all, we have to be able to replicate some variables from just one single instance into one instance per thread. Okay, so essentially it's called privatization. Or for example, in order for, let's say, 2 threads, and in order for 2 threads to execute different iterations of the loop, the 2 threads have to have a way to keep track of its own their own iteration number, and also their starting iteration and the ending iteration. So in order to do that, essentially we have to have a way to declare variables as private. Okay, so for example, private start iteration, end iteration, and I. And we have, we can have a way to declare other variables as shared, or just let them be the default. Okay, so for example, I will have to, each of the thread, we have to compute their own start and end iterations, right? So as shown in this code. After the start and the end iterations are computed by each thread can perform the computation, right? Starting from its own start iteration until end iteration. So this way they will perform different set of iterations on their own. And then the next one is that we have to wait before we go to the next loop. We want to wait until all the iterations are done. Essentially, we want to wait until both threads have finished computation of the first loop. And therefore, in order to order certain operations with respect to others, we have to put synchronization. In this case, a handy synchronization is called barrier. Barrier requires that everyone that arrives early to wait until everybody has arrived. And then once everybody has arrived, then they can go on computation. And then in the next loop, we can see that we have a problem in the sense that the sum variable has to reflect the sum of all variables in an array. So everybody has to modify the same thing. However, if everybody is modifying the same thing, we can have a problem where the threads corrupt each other's modifications. Therefore, it has to be protected by a lock and unlock. This pair essentially ensure that only one thread executes the code that is enclosed by the lock and unlock, right? And then finally we have to have a begin parallel and an end parallel to mark the beginning and the end of the code that two threads execute in parallel. Now for the message passing example, we need to have primitives of sending and receiving message. And in this case, the sending of message, we have to be selective in the sense that essentially initially the parent process has everything, right? Has all the data. We have to send only the data that is needed for computation on by the other process. So in this case, we have send message. We don't need to send the entire array B or C. Only need to send the upper half of B and the upper half of C. And the child process receives those halves. And then after both of them perform computations, actually both processes have to accumulate to their own local sum because they can't see each other memory. And at the end, we have to combine the local sums into the global one, right? So the child process, the parent process has to receive a message containing the local sum from the child process, and the child process has to send it. Once the parent process receives it, has to add its own local sum with the local sum it receives from the child process, add them together and put into the actual sum. Okay, so again, communication has to happen through messages, and there's quite a great deal of message and sending and receiving overheads. So it's good to increase the message size, and it's going to require algorithm and program modifications quite significantly because essentially the data layout, data distribution is not hidden. It's not transparent, so programmers have to incorporate that into the code. Alright, that's the end of chapter 2. In the next chapter, going to talk about the shared memory programming model techniques. Until then,